Welcome to the class. Dear students, today we are going to discuss on covalent bond. In this class we will discuss what is covalent bond. We are going to look at the examples and then we are going to see what kind of atoms show covalent bond, and then we will see what are the types of covalent bond, what are the types of classifications of covalent bond. Therein we will discuss what is a polar covalent bond, what's a non-polar covalent bond, what's a pi covalent bond, what's a sigma covalent bond, and what's a single, double and a triple bond. And lastly we are going to look at the energies of covalent bonds. So let us start. Covalent bond. Covalent bond results from sharing of one or more pair of electrons. It results from mutual sharing of one or more pair of electrons. And in the process of this mutual sharing, when they share this electron, and in the process of this mutual sharing, they achieve the stable electronic configuration in the outermost shell. What is a stable electronic configuration in outermost shell? Either it is a octet or it is a duplet. Okay, so outermost shell should have either 2 electron or either 8 electron. So when they share this electron, when there is a mutual sharing of the electron between the two atoms, they attain stable configuration, stable electronic configuration in the outermost shell, or they attain the configuration of the nearest gas, nearest inert gas. Okay, nearest inert gas can be your neon or it can be your helium. So they attain the configuration of the nearest inert gas, or they attain inert gas configuration when they go for mutual sharing of electron. So to understand the same, to understand these 2 points, let us see the covalent bond formation between H and Cl. What is the atomic number of hydrogen? 1, right? So it has got 1 electron in its outermost shell, which is the first shell. And what is the atomic number of chlorine? 17. So 287. So it has 7 electrons in its third orbit, which is the outermost shell. Correct? Now what happens is that the nucleus of this attracts the electrons of this atom, and the nucleus of this atom attracts the electrons of the hydrogen atom. Why is it so? Because the nucleus here has influence on the first shell. Correct? The nucleus here, it has got influence in the first shell, but the first shell has only 1 electron. So it can very well accommodate 1 more electron. Correct? And the nucleus here, it has influence on third shell. It has its reach till third shell. But in third shell, there are only 7 electrons. It can very well accommodate 1 electron. Correct? It can very well absorb the power of 1 electron. So the nucleus here is short of 1 electron, and the nucleus here is also short of 1 electron. So that attracts the nucleus. That attracts this nucleus towards these electrons, and that attracts this nucleus towards these electrons. What attracts? The deficiency of 1 electron in the outermost shell, because the impact is still this, right? So it is deficient of 1 more electron. Here also the impact is still third shell, but the third shell only has 7 electrons. It can very well accommodate 1 more electron, right? Its impact is still the third shell. So that is the reason why the nucleus of this attracts the electrons of this, and why the nucleus of the chlorine atom attracts the electron of the hydrogen atom. Now they come close to each other because of this attraction. But when they come close to each other, what happens is that they go for mutual sharing of electron. They go for mutual sharing of electron. And when they go for mutual sharing of electron, they achieve the inert gas configuration. Let us see how. See here, for hydrogen, duplet is achieved. It achieves the electronic configuration of helium. Correct? And for chlorine, octet configuration is achieved. It achieves the inert gas configuration of the neon gas. So inert gas configuration is achieved, or stable electronic configuration in the outermost shell is achieved. Okay, so this happens so that they can go for inert gas configuration. And why it goes for inert gas configuration we have discussed. because the nucleus here, it is short of one more electron, and nucleus here is short of one more electron. So that is why they go for a mutual sharing of electron and they become stable. So the molecule is more stable as compared to these atoms when these exist independently. Correct? Yeah. Now, another point that I wanted to discuss is what kind of atoms go for covalent bond. Okay. So there are two criteria. Number one, it should have low ionization energy, low ionization power, and number two, it should also have less electron affinity. Less electron affinity. Only atoms that have got low ionization power and less electron affinity can go for covalent bond. To illustrate this point, let me take the example of carbon. What is the atomic number of carbon? Yes, 6. Correct. What does it mean? How many number of protons are there? Proton number is how many? 6. Electron, what about electron? 6. Why? Because atomic number is 6. Atomic number is equal to the number of proton is equal to the number of electron. So the atomic number 6 means that there are 6 protons and 6 electrons. Correct? Let's draw the electronic configuration. 1s2, 2s2, 2p2. Right? Let's draw this. So it would come like this. This is the right. Now at first it would seem that the valency of carbon is 2, but what is the real valency? When it becomes activated, before going to a reaction, carbon becomes activated. When it becomes activated, the electron from this orbit, it jumps to this orbit. So it would become like this. Right? So now the valency of carbon is 4. So there are 4 electrons in its outermost orbit. That is in its second shell. There are 4 electrons. How many electrons does it need? 4 more electrons. If it gets 4 more electrons, then it will achieve octet. Or if it loses 4 electrons, right? If it loses 4 electrons, it will achieve duplet. So there are 2 options for carbon. Either to gain 4 electron or to lose 4 electron. Fine. Now, suppose that carbon has got high ionization power. Very good ionization power. Let me remind you that the proton number is 6 and electron number is 6 in carbon. Because the atomic number is 6. Now assume that carbon has got a very high ionization power. In that case, it would lose 4 electrons, right? So if it loses 4 electrons, there will be only one orbit, that will be 1s1. So carbon will be written as C4 plus. But that scenario will never occur because the number of proton is 6. Okay, the number of proton is constant, right? When it loses 4 electron would become 2. Correct? So that scenario would never occur because the protons will never lose that much electron. Correct? That this much electron it would never lose, right? So this scenario will never occur. So this is a proof that carbon is having low ionization power. Okay? Now let us see the other scenario. Let us see what happens. Assume that it is gaining. Okay? This is the right. Assume that it is gaining 4. So in that case, it will become C4 minus. So if it is gaining 4 electron more, the number of electron would become 10. So proton is constant. 6 proton would never be able to accommodate 10 electrons in its orbit. Do you think it is possible? It's not possible. It will, otherwise we have to give that much energy, okay, that much heat, so that it can accommodate 10 electron, or otherwise in normal circumstances it's not at all possible that 6 proton can take up 10 electron. It's not at all possible. That what I mean to say is carbon is having less electron affinity. Correct? So carbon has low ionization power. Low ionization power. It can never lose its electron because the proton won't allow. Number of protons won't allow. And it has also got less electron affinity. It can never gain electron because there the number of proton would not be able to accommodate that gain. So it is an example of an atom that is having low ionization power and less electron affinity. So it would neither gain electron and it would neither lose electron. Now the only option for the 4 valence electrons of the carbon is to go for mutual sharing of electron with 4 atoms, okay, or with 2 atoms, okay. So the only option that is available for carbon is to go for mutual sharing of electron. Why? What is the reason? Number 1, because carbon is having low ionization power. Protons won't allow, number of protons won't allow the loss of electrons, and also the carbon has less electron affinity because the number of protons won't be able to accommodate that much amount of electrons in it. So such atoms would go for covalent bond, such atoms would go for sharing of electron. The third point is classification. See, covalent bond is classified into 2. You already know. First is polar covalent bond and the second is non-polar covalent bond. Polar and non-polar. Non-polar. So this classification is based on the charges developed along the bond length. Okay. So in polar there are no charges developed along the bond length, and in polar there are charges developed along the bond length, and in non-polar no charge exists. I'll write non-polar here and explain non-polar first, and then I'll explain polar. So what happens in non-polar is identical atoms. This is hydrogen atom. Okay. They come close to each other. Identical atoms of same electronegativity, they come close to each other. They go for mutual sharing of electron. They go for mutual sharing of electron like this. And they go for mutual sharing of electron. The shared pair of electron is equally shared between the 2 atoms. And why is it equally shared? Because they are having the same electronegativity. They are equally shared between the 2 atoms, and the electron cloud is distributed uniformly such that no charges develop on one side, on either side of the atoms. Okay. So this non-polar covalent bond exists between, it occurs when 2 identical atoms of same electronegativity approach each other for mutual sharing of electron. The shared pair of electron lies at the center of the 2 atoms of same electronegativity. That is to say, the electron cloud is uniformly distributed, and with the result, no charges develop on either side of the atom. Examples of non-polar covalent bond is Cl2, H2, F2, identical atom, O2, N2. Okay, they are identical atoms. They come together and go for mutual sharing of electron. The shared pair of electron lies just at the center. Why? Because they are having the same electronegativity. So no side, neither of the side develop any kind of charges. Such kind of bonds are non-polar covalent bonds, and such compounds are called as non-polar covalent compounds. Now let us go for polar. Non-identical atoms, okay, they come close to each other, they approach each other, okay, they approach each other, and what happens? Non-identical atoms, they approach each other, and the orbital, the newly formed orbital, they are having what? They have, there is a non-identical atoms of different electronegativity. Non-identical atoms of different electronegativity, they approach each other, they go for mutual sharing of electron, and the shared pair of electron is deviated or is oriented towards the more electronegative atom. That is to say, the electron cloud shifts towards the region of higher electronegative atom. Okay, example of this is say HCl, HF. Okay, what happens in HCl? See, Cl is having higher electronegativity, F is having higher electronegativity. Are they identical? No, they are non-identical atoms. They came close to each other. For what? For sharing their pair of electrons. Right? Hydrogen had one, Cl has one. Of course, Cl has other 7. Right? So they came together, they shared. In this, when they shared, they achieved their objective. Hydrogen got duplet configuration in outermost one orbital, and chlorine got octet configuration in the third orbit. So both objectives were met, but the shared pair of electron was not shared equally. It was more towards chlorine, and with the result, the cloud was more oriented towards chlorine. The electron cloud was oriented towards chlorine, and with the result, the region around the electronegative chlorine, it developed negative charge, and the region around the electropositive hydrogen, it developed positive charge. Correct? So now this polarity is along the bond length. This polarity is along the bond length. That means that as you go from this position to this position, the magnitude of negative charge would increase. So the polarity is along the bond length. Such kind of such kind of bonds are called as polar covalent bonds. The exact measure of this polarity is given by dipole strength. It's given by dipole moment, which is represented by mu. Its unit is dB. So higher the dipole moment, it would mean that higher the polarity, and lower the dipole moment would mean lower is the polarity. Okay, so to know more about dipole moment and polarity, please refer my earlier video wherein I have discussed it in detail. The title of the video is Polarity and Dipole Moment. So we have seen here that covalent bond is of two types depending upon whether charges are developed along the bond length. The first is non-polar. Here identical atoms of same electronegativity approach each other. The shared pair of electron is shared equally, and the cloud is uniformly distributed. No charges develop. Examples we have given. Here we have said that non-identical atoms of different electronegativity go for sharing of electron. With the result, the shared pair of electron is towards the more electronegative atom, and with the result, the cloud is oriented towards the more electronegative atom, and because of this, polarity develops. Region around the electronegative atom becomes negatively charged, and the region around the electropositive atom becomes positively charged. This polarity is along the bond length. That is, if you go from this side to this side, negative charge would increase. This is expressed by dipole moment, the unit of which is dB. So this is the third point. Covalent bonds. The fourth point is, let me come to the fourth point now. Fine. The fourth point is that based on the type of overlap, covalent bonds are divided into two. One is the sigma covalent bond, the other one is the pi covalent bond. Let us now discuss sigma covalent bond. Sigma covalent bond is because of head-on overlap. Head-on overlap. It is because of head-on overlap. This head-on overlap can be between an s and s orbital, right? and s and s orbital can go for head-on overlap. Example is H2, right? It can be between p and p orbital, p and p orbital. Okay, example is O2, correct? It can be between s and p orbital, s and p orbital. Sorry for that. It can be between s and p orbital. Example is HCl or HF. These are head-on overlaps. It can also be, this is the example, sigma bond overlap, sigma covalent bond. It is occurring because of head-on overlap between orbitals. This head-on overlap between orbital, it can be between an s and s orbital. Example H2. It can be between a p and p orbital. Example is O2. It can be, or F2, okay, or Br2. It can be between s and p orbital. Example is HCl and HF. It can also be between the sigma bond overlap. It can also be between this thing, right? This is sp2 hybridized carbon atom. sp2 hybridized carbon atom. Alkene, correct? sp2 hybridized carbon atom. In this condition, sp2 hybrid orbital can overlap, head-on overlap with sp2 hybrid orbital of another carbon atom, correct? This is sp2 hybrid orbital, this is sp2 hybrid orbital. So sp2 hybrid orbital overlap can occur between two carbon atoms in an alkene. So this is also an example of head-on overlap. Here also sigma bond can come. It can also occur between sp2 hybrid orbital of carbon and s orbital of hydrogen. So this is an example of head-on overlap, sp2 and s orbital overlap. This is example of sp2 hybrid orbital overlap. All these are examples of head-on overlaps. Okay. It can also occur between sp2 hybrid orbital of alkene and p orbital of chlorine or fluorine, right? So sp2 hybrid orbital, p orbital, head-on overlap, correct? So these are examples of head-on overlap involving sp2 hybridized carbon atom. Head-on overlap can occur between sp2 hybrid orbital of one carbon with the sp2 hybrid orbital of another carbon, resulting in a sigma bond. It can also occur between sp2 hybrid orbital of carbon and s orbital of hydrogen, resulting in sigma bond. It can occur also between sp2 hybrid orbital of carbon and p orbital of fluorine, chlorine or bromine. So these all are examples of sigma bond, sigma covalent bonds, right? Similarly, for alkynes also, this is alkyne, a linear shape, right? It has got two unhybridized orbitals, p orbitals, py and pz. Here also you can see head-on overlap, but this head-on overlap is between sp hybrid orbital of one carbon and sp hybrid orbital of another carbon. So sp overlap can occur, head-on overlap can occur, and this can result in sigma bond. Here also you can see that sp hybrid orbital and s orbital of your hydrogen. So sp-s head-on overlap can be also occur. If in this place there is a p orbital of your fluorine or chlorine, then it will become sp-p hybrid orbital, head-on overlap. sp-p head-on overlap. So these are all examples of your sigma covalent bond. Okay, in these ways sigma covalent bond occurs or it can happen. That is, it only requires head-on overlap. This head-on overlap can be between S and S orbital, it can be between S and P orbital, it can be between P and P orbital, it can be between sp2 hybrid orbital, it can be between sp2s hybrid s orbital, it can be between sp2 and p orbital. Here we have seen it is between sp orbital. Here sp-s orbital we say. Now we are seeing sp-p orbital if it is fluorine or chlorine. So all these are examples of head-on overlap, and this can result in a sigma covalent bond. All what is required is head-on overlap. Now let us go for pi bond. Pi bond, just change the marker. Pi bond. What we are seeing in pi bond? Parallel overlap of unhybridized p orbital. Parallel overlap of unhybridized p orbital. You can see here there are two unhybridized p orbital. One is the py and the pz. So they go for parallel overlap. Fine. They go for parallel overlap, and that could result in pi bond formation. That would result in pi bond formation. So pi bond occurs between, it is only sideways or parallel overlap, sideways overlap or parallel overlap of p orbitals. Only p orbitals will go for pi bond formation. That too, most commonly we are seeing unhybridized p orbital. Otherwise also without hybridization also it can occur. For example, your fluorine or oxygen, okay, and chlorine. Okay, these are not, one is sigma bond, one is because of head-on overlap of p orbitals. Okay, so one is sigma bond because of pp head-on overlap, and one is pi bond because of pp sideways overlap. Okay, this does not require hybridization. So it can be between unhybridized p orbital, or it can be between hybridized p orbital. This sideways overlap can occur between unhybridized p orbital, or it can occur between hybridized. This is occurring between unhybridized p orbital. So we have seen example here. We can see side-on overlap in alkene and alkyne. Also, it also occurs between unhybridized p orbital. So for pi bond formation, we require unhybridized p orbital. It occurs in unhybridized p orbital. We have seen lot of examples. For example, your fluorine, the second bond is made like that. Oxygen second bond is made like that. Chlorine second bond is made like that. Your ethene and your ethine second and third bond are made like this. Okay, because of overlap of unhybridized p orbital. So there are two kinds of covalent bonds, the sigma covalent bond and the pi covalent bond. So if you are asking me which is more strong, is the sigma bond more strong or a pi bond more strong, then I would say that sigma bond is much stronger, because sigma bond, it is closer to nucleus. This is the sigma bond. Look at the sigma bond. The extent of overlap in a sigma bond is much great. The extent of overlap in a sigma bond is greater, and because of this, the electrons, no, this actually becomes like this. Just see the extent of overlap. The electrons, they are delocalized over a very small area, and that small area, that area where the electrons are delocalized, that small area is also under very close vicinity of nucleus. So that makes the sigma bond extremely stable. That makes the sigma bond very hard to break. So if you are breaking sigma bond, more energy will be released. So sigma bond is much stronger. If you are seeing your pi bond, pi bond formation, look at this pi bond. It is occurring because of your sideways overlap, right? So what would happen? This is the nucleus. Okay, this is the nucleus part. So this part will combine and this part will combine. So now we got like this. The nucleus is still here. See. So we are going for parallel overlap. So when parallel overlap occurs, the extent of overlap is not so much. Look at this. The extent of overlap is less, and the electrons, where the probability of finding the electron is greatest, is spread over a large surface area. The delocalization of electron is on a large surface area, and also it is not under close vicinity of nucleus. So that makes this more unstable compared to sigma bond. So less energetic. So it is very easy to break a pi bond rather than a sigma bond. Correct? Because pi bond can be easily broken because it is not under the close scrutiny of the nucleus. Correct? It is not under the close monitoring of nucleus. But a sigma bond is under a close vicinity of nucleus. It is under the close scrutiny of nucleus, and that would be very difficult to break a sigma bond. But because the pi bond electrons are not in the close vicinity of nucleus, they are not under the total control of nucleus. So they can be easily broken. Other than that, there is another way of classifying covalent bond. One is depending upon the pairs of electron shared. Pairs of electron shared. See, if there is only one pair of electron shared, then that makes it a single covalent bond. If there are two pair of electrons shared, it would be a double covalent bond or a double bond. If there are three pair of electrons shared, that would be a triple covalent bond or a triple bond. Single bond has sigma bond, one sigma bond. Double bond has one sigma and one pi, and triple bond has one sigma and two pi. If you are asking me which is the most strongest, then I would say triple bond collectively is more strong because it is having one sigma and two pi. Right? But individually, if you are asking me, then sigma bond is the strongest. But collectively here triple bond is strongest because it is having one sigma and two pi bonds. Triple bond is shortest among all, and being shortest, it is very hard to break, saying that it is a very high amount of energy is required to break the triple bond rather than a single bond. Why? Because it is having more number of bonds. Simply because it is having more number of bonds, it is collective, it is more strong. So this is the classification. Let us now go to energetics part, and we will just simply write down some of the covalent bonds that we know and its energy. The carbon-carbon single bond. Let me take the blue marker. The carbon-carbon single bond has 80 kilocalorie mole of energy. Carbon-carbon double bond is having 145 kilocalorie mole. Carbon-carbon triple bond is having 200 kilocalorie per mole. Fine. The hydrogen-hydrogen bond is having 105 kilocalorie per mole. The hydrogen Cl bond is having 103 kilocalorie per mole of energy. OH bond is having 110 kilocalorie per mole. CO bond is having 86 kilocalorie per mole, and carbon double bond O is having 190 kilocalorie per mole. All these values are in kilocalorie per mole. Kilocalorie per mole. So we are seeing carbon-carbon single bond 80 kilocalorie per mole, carbon-carbon double bond 145, triple bond 200, HH 105, HCl 103, OH 110, CO 86, C double bond O 190 kilocalorie per mole. That much energy is required to break 1 mole of these bonds. Dear students, I hope you have understood and you have liked the class. If you have done so, please do not forget to subscribe the channel, do share it and like it. Thank you very much.